In this video, we will look at 5 technology advances that matter right now because they are crossing an important threshold, from research project to practical platform. The big question is not only what these technologies can do, it is how they will combine and how quickly people, companies, and governments can use responsibly. The first major advance is agentic artificial intelligence. Traditional software waits for a user to click a button. A chatbot waits for a prompt. An AI agent goes a step further. It can plan a task, choose tools, search information, write code, compare options, and series of actions toward a goal. That does not mean agents are magically reliable. They still need guardrails, review, and clear permissions. But the direction is important. AI is moving from answering questions to helping run workflows. In business, that might mean an agent that monitors supply chains, drafts reports, checks, invoices, or helps customer service teams solve problems faster. In science, it might mean an assistant that reviews papers, proposes experiments, and results. The breakthrough is not one model alone. It is the combination of reasoning, tool use, memory, and integration with real systems. The next wave of productivity may come from teams where people set goals and standards. Handles more of the repetitive coordination work. The second advance is physical AI, smarter robots that can understand and act in the... For decades, robots were excellent at repetitive factory work, but fragile and messy. A warehouse, a hospital, a farm, or a home is different. Objects move, lighting changes, people behave unpredictably. Recent progress in computer vision, simulation, reinforcement learning, helping robots generalize. Instead of programming every motion by hand, engineers can train robots to recognize, follow language instructions, and learn from demonstrations. This matters because many economies face labor shortages in logistics, elder care, agriculture, and manufacturing. The goal is not just humanoid robots, it is useful physical automation, inspection drones, surgical assistants, warehouse, agricultural robots, and machines that can work safely around people. The challenge is safety, cost, and reliability. A robot that works 90% of the time is impressive in a demo, but not enough in a hospital or on a factory floor. The real advance is the move toward robots that can adapt without becoming unpredictable. The third advance is quantum computing. Quantum computers use the behavior of quantum systems to process information in ways that classical computers cannot easily copy. For years, the field has been full of promise, but also full of caution. The machines are difficult to build, errors are common, and most useful applications ahead of us. But recent results show real movement. Researchers are demonstrating more verifiable quantum advantage, better error correction, more realistic paths toward chemistry and material simulation. Why does that matter? Because nature is quantum. Molecules, catalysts, superconductors, and many battery materials are hard for ordinary computers to model exactly. A practical quantum computer could help scientists explore better drugs, cleaner chemistry, stronger materials, and more efficient energy systems. We are not at the point where quantum computers replace laptops or cloud servers. That is the wrong mental model. The more realistic picture is specialized quantum machines working alongside AI, solving narrow but extremely valuable scientific problems. The key signal is that the field is shifting from spectacle toward usefulness. The fourth advance is bioengineering, specially engineered living therapeutics. Medicine has already been changed by sequencing, gene editing, mRNA platforms, and therapies. The next step is more programmable biology. Instead of treating the body only with small molecules, scientists can engineer cells or genetic instructions to sense conditions and respond. Imagine a living therapeutic that detects inflammation and releases a treatment. Engineered immune cells that better recognize cancer or microbes designed to support the precise ways. This area is powerful because biology already manufactures complex molecules, repairs, and adapts to changing environments. The engineering challenge is to make those abilities predictable, safe, and controllable. There are serious questions about regulation, access, long-term effects, and biosecurity. But the potential is enormous. Bioengineering could reshape healthcare, agriculture, climate resilience, and production. It also connects with AI. Better models can help design proteins, predict molecular behavior, and accelerate. The result is a new kind of technology stack where code, data, and living systems begin to overlap. The fifth advance is next-generation energy and materials. Many digital technologies depend on a physical foundation: chips, batteries, power grids, cooling systems, and rare materials. As AI data centers grow, electric vehicles spread, and climate pressure rises, energy becomes strategic. One exciting area is structural battery composites. Instead of treating a battery as a separate heavy block, researchers are exploring that can carry load and store energy at the same time. In the future, parts of a car, drone, or aircraft could become part of the battery. Other advances include solid-state batteries, better grid storage, advanced nuclear designs, low-carbon cement, and materials discovered with the help of AI. The common theme is efficiency, doing more with less mass, less waste, and lower. This is where deep tech becomes visible in everyday life. Better batteries mean longer range and faster charging. Better grids mean more reliable, clean power. Better materials mean lighter machines and more resilient infrastructure. The energy transition is not one invention. It is a stack of thousands of improvements that have to scale.